Chalo, start karte hain. Look, it's the final lap for NEET and JEE, and getting a solid grip on the laws of motion is, well, it's non-negotiable. So in the next few minutes, we're going to make every single core concept from this chapter absolutely crystal clear. Ready? Let's dive right in.
So get ready for this super quick masterclass. And hey, if you find this revision style helpful, you know what to do. Don't forget to like and subscribe. All right, let's start with a really simple question. You kick a football, right? It rolls for a bit, and then it stops. Why? I mean, it seems obvious now, but this very question puzzled some of the smartest minds for centuries. Well, the ancient Greek thinker Aristotle had a guess. He basically said, to keep something moving, you need to keep pushing it. And you know what? That kind of feels right, doesn't it? Think about a toy car. You have to keep pulling the string to make it go. If you let go, it stops. But here's the catch. This idea is actually flawed. The real breakthrough? That came from Galileo. He asked a brilliant question. What if there was no friction at all? See, if you could get rid of friction, an object that's moving would just keep moving. Forever, with a constant velocity. The football stops because of the real villain here, friction from the ground and the air pushing against it. And this tendency of a body to just keep doing what it's doing, that's called inertia. All right, so building on Galileo's foundation, Sir Isaac Newton came along and gave us the 3 golden rules of mechanics, the rules that can solve pretty much any problem you'll face. So Newton's first law is pretty much Galileo's law of inertia, just formalized. In simple terms, if the net external force on a body is 0, then its acceleration is also 0. That's it. The body wants to stay as it is. If it's at rest, it stays at rest. If it's moving uniformly, it keeps moving uniformly. You can think of it like this. The body is lazy. Let's connect this to real life, something you've definitely felt. You're standing in a bus that's stopped. Suddenly, it lurches forward. What happens? You get thrown backward, right? Why? Because your feet move forward with the bus, but your upper body, because of its inertia of rest, wants to stay right where it was. Okay, so the first law tells us what a force does. It changes the state of motion. The second law tells us how to measure that force. Newton's actual statement was that force is directly proportional to the rate of change of momentum. And you know momentum, P, is just mass times velocity. So what we're really saying is F equals dP by dt. Now we all know and love F equals ma. But listen carefully, that's a special case. It only works when the mass is constant. The real, the original, the BOP formula is F equals dP by dt. For things like rocket propulsion where the mass is changing, this is the one you gotta use. For NEET and JEE, knowing this difference is absolutely critical. And now for the most famous law of them all. You know it by heart. For every action, there is an equal and opposite reaction. Think of a rocket. It pushes hot gases down, that's the action. And the gases push the rocket up, that's the reaction. Seems simple, right? Well, here's where so many students get tripped up. If the forces are equal and opposite, why doesn't everything just cancel out? How does anything move? The secret is they act on different bodies. The earth pulls you down, that's the action, on you. But you also pull the earth up, that's the reaction on the earth. One force is on you, the other is on the earth. They can't cancel each other out. Just remember this, allegoric bodies pay. Okay, let's wrap up the 3 laws in one quick summary. The first law defines force. It's about inertia. The second law measures force. It's about cause and effect, F equals dP/dt. And the third law describes the nature of force, that they always come in action-reaction pairs. Seriously, take a screenshot of this table. It's perfect for a last-minute revision. So we've understood the laws, but how do we actually use them to solve problems? There's one tool that is the master key to everything in mechanics, the free body diagram, or FBD. Drawing an FBD is as easy as 1, 2, 3. Step 1, isolate the body. Just draw it all by itself. Step 2, mark all the external forces acting on that body. Use arrows to show weight, tension, normal force, everything. And step 3, choose your axes and apply the golden rule. F net equals ma. That's it. Of course, to mark the forces on an FBD, you have to know what they are first. So let's do a quick roll call of the everyday forces you'll be dealing with. Broadly speaking, you can split forces into 2 main families. You've got your contact forces, the ones that need to touch something like friction, tension, or the normal reaction. And then you have the non-contact forces, the ones that act from a distance like gravity or magnetism. Okay, let's talk about friction, because this is where a lot of confusion happens. First, there's static friction. This acts when an object is about to move but isn't moving yet. It's a clever, self-adjusting force that goes up to a maximum value of μs times n. But the moment the body starts sliding, static friction disappears and kinetic friction takes over. This one has a constant value, μk times n. And the most important thing to remember, the static coefficient, μs, is always greater than the kinetic one, μk. All right, theory's done. Let's look at some of the biggest problem hotspots for NEET and JEE, the places where these laws are applied again and again. Lift problems. A classic. It's all about apparent weight, what you feel your weight is. When the lift accelerates up, you feel heavier, right? That's because your apparent weight is m times g plus a. When it accelerates down, you feel lighter, because it's m times g minus a. And what if the cable snaps? In free fall, you'd feel totally weightless. Your apparent weight would be 0. Here's another huge topic. For any object to move in a circle, there must be a force constantly pulling it towards the center. Now listen, this is not a new type of force. It's just a requirement. We call this required force the centripetal force, and it's equal to mv squared over r. So, where does this centripetal force come from? Well, something has to provide it. When a car takes a turn on a flat road, it's the static friction between the tires and the road that provides this inward pull. And to avoid slipping, there's a simple condition. Your speed squared has to be less than or equal to μs times r times g. This gives you the direct formula for the maximum safe speed. All right, here we go. Time for the final rapid-fire punch of key takeaways. And to finish, I want to leave you with a classic puzzle to think about. If a horse pulls a cart forward, that's the action. Then the cart must pull the horse backward with an equal force. That's the reaction. So, how does the horse-cart system ever move forward? Think about it. Here's a hint. Draw the FBDs and focus on the external forces. The answer is hidden in the very laws we just discussed. And that is your super fast revision of the laws of motion. I really hope that helped clear things up. For more quick revision explainers just like this one, make sure you're subscribed. All the very best for your exams.